Now we turn to merge sort. It takes a very different path. It splits the array, sorts each half, and then merges the sorted halves back together. Now let's meet merge sort. It has three simple moves. Split the array in half, sort each half on its own, then merge the two sorted halves back into one. Think of two piles of graded exams. Each pile is already sorted by score. To make one combined sorted pile, you look at the top paper of each pile, take the lower one, and repeat. Each step is one small comparison. The base case is tiny. An array of 0 or 1 element is already sorted, so there is nothing to do. The recursive case does the splitting. We sort the left half, then sort the right half, each the same way. Then we combine. We merge the two sorted halves into one longer sorted run. The key idea is simple. All the real comparing happens in the merge step. The recursion only decides which two sorted runs to merge next. This picture shows the whole recursion as a tree. The full array sits at the top. Each step below it splits an array into two halves. The top array splits into a left half and a right half. Each half splits again and again until every piece holds just one element. The green boxes at the bottom are the base cases, size 1 or less. Because we always cut exactly in half, the tree is log base 2 of n levels deep. Then the merges climb back up. Here is the property that makes merge sort predictable. This tree shape never degrades. Merge sort always splits exactly in half, so its recursion depth is always log base 2 of n, no matter what order the input arrives in. Quicksort's tree, coming next, has no such guarantee. Let's read the pseudocode. Merge sort is the recursion. If low is less than high, there is more than one element, so we find the midpoint. Mid is low plus high minus low over 2. Then we sort the left half, sort the right half, and merge the two sorted halves. Now look at merge. It uses three cursors. I starts at low and walks the left half. J starts at mid plus 1 and walks the right half. K writes into the aux array. While both halves still have elements, we compare their two heads. If A at index I is less than or equal to at index J, we copy from the left. Otherwise, we copy from the right. Using less than or equal, not less than, keeps equal keys in their original order, so the sort stays stable. At the end, we copy any leftovers, then copy aux back into A. Let's trace one merge step by step. We have two sorted runs. The left run is 3, 27, 38, 43. The right run is 9, 10, 82. Each row copies one value into aux, the second array. We always take the smaller of the two current heads. Before we start, predict which head goes first, 3 or 9. Step 1. The two heads are 3 and 9. 3 is smaller, so we copy 3 from the left run. The amber cell shows the value we just took. Aux is now 3. Step 2. The left head is now 27 and the right head is still 9. 9 is smaller, so we copy 9 from the right run. Aux is now 3, 9. Step 3. The heads are 27 and 10. 10 is smaller, so we copy 10 from the right run. Aux is now 3, 9, 10. Step 4. The heads are 27 and 82. Now 27 is smaller, so we copy 27 from the left run. Aux is now 3, 9, 10, 27. Step 5. The heads are 38 and 82. 38 is smaller, so we copy it from the left run. Aux is now 3, 9, 10, 27, 38. Step 6. The heads are 43 and 82. 43 is smaller, so we copy it from the left run. That empties the left run. aux is now 3, 9, 10, 27, 38, 43. Step 7. The left run is empty, so we just drain the one value left in the right run, 82. Aux is now the full sorted run. Then aux is copied back into A. A quick check on that merge. Which run's head was copied into the auxiliary array first, the 3 or the 9, and why? Pause and answer. The answer is 3, the left run's head. The very first comparison is 3 against 9, and 3 is smaller, so it goes first. A second check, this one about the invariant. Is merge sort stable, and why does that matter? Pause and think. The answer is yes. The merge steps tie rule takes from the left run on equal keys, using less than or equal. So an element that started earlier never gets placed after an equal element that started later. And here is why it matters. Whenever records are sorted by one field, and a second field's original order should survive. For example, sorting log entries by severity while keeping same severity entries in timestamp order. This is merge sort in C. The merge function takes the array a scratch array called aux, and the three indices low, mid, and high. We set I to low, j to mid plus 1, and k to low. I walks the left half, j walks the right half, and k writes into aux. While both still have elements, we keep merging. We compare the two heads. If A at index I is less than or equal to that index j, we copy at I into aux. Otherwise, we copy A at j using less than or equal. Not less than keeps equal keys stable. When one half runs out, the other may still have values. If the left half has leftovers, we copy them straight into aux. And if the right half has leftovers, we copy those too. Then mempy copies the merged run from aux back into A, so it now holds the sorted result. The merge sort function is the one you call. It takes the array and its size n. If n is less than 2, the array is already sorted, so we return right away. We allocate the aux array once, big enough for the whole array. The recursive helper then sorts the whole range, from 0 to n-1. When it finishes, we free aux. This function owns aux, so it frees what it owns. Merge sort's cost is the same in every case. Best, average, and worst are all big O of n log, and the balanced tree guarantees it every time. It is stable, and it is not in place. It needs big O of n extra space for the auxiliary array. Now the trade. You may think merge sort simply beats quicksort, because it has no big O of n squared worst case. But it pays big O of n extra memory that quicksort never needs. And on large in-memory arrays, that second array is exactly why quicksort is often preferred anyway, despite its worst case. The full program allocates the auxiliary array once per call, and frees it before returning.